The title is Deep RetiSignet, an automated AI-based framework for retinal disease diagnosis. The manuscript ID is 9511. First, we'll be starting with our contributions. So the first contribution is we have developed a deep RetinaNet framework for simultaneously extract in-depth features from retinal fundus images. Is capable of retaining the vessels along with the disease category identification. The developed deep RetiSignet framework comprises of two networks. One is RetiSignet and the second one is STDeepNet networks for vessel extraction and disease categorization respectively. The designed RetiSignet framework provides better performance for on-scene dataset. For disease classification, the proposed STDeepNet is capable of retaining subtle details, and the usage of skip connections makes the model more robust. In the STDeepNet network, a multi-stage feature fusion mechanism is proposed to further enhance the disease identification motivations. In the motivation from recent literatures, it can be found that the state-of-the-art techniques are incapable of extracting subtle details from the fundus images. The SOTA approaches are unable to handle the on-scene setup due to diverse variations in the disease categories. The vessel extraction capability of SOTA approaches are poor due to complexities and presence of subtle features in the fundus images. Proposed method. So first of all, whatever the models we have developed, those models have been trained by using 5 dataset. So this is the original 5 dataset as you can see. So in the first stage, we have extracted green channels, and the dataset itself will be containing 4 different classes of images like AMD, DR, glaucoma and normal. Again, the same dataset, we have ground truth for the retinal vessels as you can see. Next, the segmentation is done, or particularly the vessel extraction is done by using RetiSignet, which is having 2 sub networks. One is the AEDnet and the second one is residual quadrant. So this is the segmented binary vessels which are extracted from the proposed RetiSignet. Next, we have found the max segmented images. Further, these 2 original green channel images along with the ground truth are fused, and the fused images are given as the training images to the classification network, that is STDeepNet. Again, the extracted vessels along with the green channels are again fused, and these fused images are taken as the testing images for the classification networks. And finally, the network is tested on those images to find different classes of diseases like AMD, DR, glaucoma and normal. These are the results you can see. The first row is containing the input images, the second row is for the ground truth, the third row is the segmented vessels, and the fourth one is maxed images. And as you can see, the last 4 rows are the images for 4 columns, particularly are the images for the 5 dataset, and first 3 columns are the images for the Chase, DV1, Stair and Drive datasets respectively. And these are few comparison, and as you can see from the comparison table, whatever the dice coefficient particularly, which is very important for vessel extraction, we have found it is superior as compared to other SOTA approaches what we have given in the references. Similarly, these are the results found, the results for the confusion matrix found for different data sets like RFMID, ODIR and 5s in 1A, B and C respectively. And these are the few results. As you can see, the accuracy from our method for all these 3 datasets like 5, RFMID and ODI are superior as compared to other approaches. Conclusion and future scope. In the first part, we have seen the developed RetiSignet can effectively extract the vessels. Our AEDnet is efficient for detecting the vessel boundary, and quadrant network is capable of retaining global features. The disease classification task is carried out by using STDeepNet network consisting of MI, MCOM blocks and LSTM layers. The MI and MCOM blocks can accurately preserve the subtle details variation in the fundus images. Also, the LSTM layers can effectively capture the image's long-term dependencies and contextual relationships. The design model is capable of handling various complex datasets, including 5-layer drives, trace, DB1, RFMID, and ODIR efficiently. From various SOTA, we have seen that the proposed method, deep retina net surfaces, 49 recently developed state-of-the-art approaches. However, the particular network is computationally expensive, and further the developed network needs to be validated for on-scene dataset of hence on-scene data, particularly for the classification purpose. Hence, in future, we would like to reduce the computational complexity of the framework along with improving the network for more disease category identification on-scene setup. Thank you.